Let's have a little discussion on Cramers rule. This can be used to solve simultaneous equations, whether it's 2 by 2, 3 by 3, and so on. All right, using matrices. Now, suppose you have two equations. You have AX plus BY equals R, and you have CX plus DY equals S. All right. Now, using the elimination method, suppose you multiply equation 1. This is equation 1 and this is equation 2. Let's multiply equation 2, equation 1 by C, and then equation 2 by A, so that we have the same number times X. Then we eliminate X. So what we have is equation 1 multiplied by C. So we have C by A. So we have ACX plus C times B. So we have BCY equals C times R, CR. Good. Then we have equation 2 by A times C. So we have ACX plus A times D, ADY equals, and then here we have A times S. So we have AS. Now let's call this equation 3 and this equation 4. Let's subtract equation 3 and 4. Equation 3 minus equation 4. ACX minus ACX is 0. X is eliminated. BCY, so we have BCY minus ADY, ADY equals CR minus AS. All right. We factorize, put y outside the bracket, and then what we would have is that we have y open bracket BC minus AD equals CR minus AS. So if we transpose for y, we get y equals, we make y the subject here. So we have CR minus AS divided by BC minus AD. Now, this is also the same thing as AS minus CR over AD minus BC. If we multiply both numerator and denominator by -1, we get the same thing here. All right. So we have y. Let's put that aside. So you know that y is equal to, let's write this one, AS minus CR over AD minus BC. All right. So we have that. Now, let's go back to what we were doing before. I'm going to erase from this level down, and then we will eliminate y this time. All right, so let's do that. Now, to eliminate y, we want the same numbers y in equation 3 and 4, and we're going to subtract them. So let's say we're going to multiply equation 1 by d, and then equation 2 by b. So we're going to end up with a b dy in both equation 3 and 4, and we subtract them. So equation 1 by d, we have ad, it will be x plus bd y equals rd, dr. Let's keep it in alphabetical order. All right, this is equation 3. Then equation 2 by b now, b times c, we have bcx plus bdy equals b times s, bs. Let's call this equation 4. Now, equation 3 minus equation 4, we're going to have adx minus bcx. Then we're going to have bdy minus bdy. But if we put bdy minus bdy, they disappear. It subtracts itself, so we don't need to write it down here. Let's just leave it out. Equals, and then dr minus bs. dr minus bs. Okay. If we factorize and put x outside the bracket now, we have x open bracket ad minus bc equals dr minus bs. So when we make x the subject of the formula, what we're going to have is x equal. It's going to be dr minus bs over ad. Let me rewrite that. ad minus bc. Okay, so we have our x and y over here. All right. Now let's just erase these, and then we examine these two results we got. Now, we saw that x is equal to dr minus bs over ad minus bc. Now, suppose we consider dr minus bs as the determinant of a matrix. That matrix would be what? It would be D up here, R down here, where it's dr minus B up here, S down here. Alright? So you see that? Now, it could also be that, let's examine that later on. We're going to make an adjustment to it. AD minus BC would be A up here, D down here, minus BC. I had put a round bracket, it's a straight line. Alright, now if we put R up here, dr is the same as rd, so it's r times d minus bs over a, b, c, d. Now, let's look at this. You notice that here you can consider this BD is this same BD. You see that? But the RS now, you remove the AC from here. And you take this RS and put here. You see that? So if you remove the AC and put RS there, you would have RS, R up here, S down here, B up here, as in this case, D down here, as in this case. So you would have R here, S here, R here, S here, B, B, D, D. You see that? So if you change the column, if you rewrite these as matrices, and you say A, B, C, D, then you change this column AC to the elements in the answer RS, you get this determinant, and this is over AB, A, B, C, D. When you write A, B, C, and D as a column matrix, you have it like this: A, B, C, D. Notice it's the same thing as you have here, A, B, C, D. Right? So basically, what you're doing, first of all, it would have been AC up here, A would be up here, C would be down here. You change it to RS. So you erase the A and C and put RS instead. So you see that? Now, that is X. Let's see what Y is. Let's scroll up a bit and we'll look at Y. This is saying that Y is AS minus CR. So Y is equal to AS. This AS could be, let's write it down here first. AS minus CR over AD minus BC. Alright, this AS here, if you consider the determinant of a matrix, it will be A up here, S down here, CR would be R multiplied by C over AD minus BC. So A, D, A, B, C, D, A, B, C, D. The determinant here would be AD minus BC. You see that? Now, you see the A, B, C, D. If you wrote this before as A, B, C, D, then you change the second column, the elements in the second column, to RS. So you erase the B and D and put in RS instead, and you get the same determinant here, AS minus CR. So the determinant here would be A times S minus C times R. Okay, good. So that is a discussion of Cramers rule, which shows how it is developed and the proof of Cramers rule. We're going to look at using it to solve examples of simultaneous equations. So I will see you then.